You woke up today, checked your phone, maybe watched your position glide smoothly across a map as if the planet itself were a simple board game. Somewhere far above you, satellites corrected their clocks by tiny slices of a microsecond, so your route would not drift into the ocean. Those corrections only work because of something called spacetime. We have photographed spacetime bending around black holes. We have listened to spacetime ring like a drum when distant stars collide. Yet if you ask physicists what spacetime actually is, the honest answer is unnerving. We do not know. If you enjoy exploring mysteries that are both practical and mind-bending, tap like, subscribe, and stay with us. Let us start with the weirdest part. Spacetime is not just a poetic word scientists use in public talks. It is a literal ingredient in the equations that govern gravity, motion, and the structure of the universe. It decides how planets orbit, how light travels, and even how fast your wristwatch ticks. Your phone would get lost without it. Gravitational wave observatories depend on it. The iconic images of black hole shadows glowing in radio light are, in a very real sense, portraits of curved spacetime. And yet behind all that engineering and all that triumph sits a blank area in our understanding where the label simply says fabric unknown. For most of human history, we thought of space and time as completely separate things. Space felt like a stage, 3 directions you can walk or fly through, left, right, forward, backward, up, down. Time felt like a universal river flowing at the same rate for everyone, no matter what. Isaac Newton built a stunningly successful theory of motion and gravity on that foundation. In his picture, the universe is like a clockwork running on absolute time, with objects moving through an invisible, unchanging grid of space. It matched observation so well that for more than 200 years, no one had a serious reason to doubt it. Then Einstein arrived and quietly set that picture on fire. By insisting that the speed of light is the same for every observer, he discovered that time cannot be absolute. Clocks run at different rates depending on how they move. Distances shrink along the direction of motion. Space and time fuse into a single 4-dimensional structure that responds to energy and mass. General relativity, the later expansion of these ideas, says that gravity is not a force pulling things together, but the geometry of space-time itself. Planets, light beams, and even you at your desk are simply following paths through a curved fabric. That is already strange, but it is not the deepest weirdness. The deeper problem is that this beautiful picture, which has passed every experimental test we have thrown at it, seems incomplete in at least 3 enormous ways. First question, what is space-time made of, if it is made of anything at all? Second question, what truly happened at the beginning of the universe when the equations point to a singularity where density and curvature blow up to infinity? Third question, do black holes destroy information in a way that breaks the basic rules of quantum mechanics? Or does spacetime somehow hide and then release that information in a way we do not yet grasp? These are not questions for late-night philosophy clubs alone. The first question matters because quantum mechanics tells us that almost everything in nature comes in discrete units, yet we still treat spacetime as infinitely smooth. If the fabric is actually grainy at unimaginably tiny scales, it would rewrite how we think about distance, duration, and even cause and effect. The second question matters because the story of the cosmos that we tell in textbooks and planetarium shows begins with an event our main theory cannot actually describe. The third question matters because if information really can vanish into a black hole, then our most precise theory of the microscopic world stops being trustworthy. At the same time, this mysterious fabric is all over your daily life. Global Positioning System satellites bend their timing around the curvature of space-time so your blue dot lands on the correct street. The colour of gold and the liquid nature of Mercury both rely on relativistic effects that arise because electrons near heavy nuclei dance through space-time at a significant fraction of light speed. Fibre optic cables and high-speed communication networks quietly adjust for time differences that come from motion and gravity. When the Laser Interferometer Gravitational Wave Observatory detected its first signal, that tiny wiggle in laser light was space-time itself, stretching and squeezing as ripples from colliding black holes pass through Earth. This creates a strange split in our relationship with reality. On one side, space-time is a trusted workhorse. Engineers treat Einstein's equations like a well-tested toolkit. Plug in the numbers, get the answer, Watch the rocket arrive at the right place. On the other side, spacetime is a concept we only half understand, a kind of invisible medium whose underlying nature we have never touched. It is as if we had built a thriving global industry around sound wave, while having no idea that air is made of molecules. We can use the waves perfectly, yet the material that carries them remains a mystery. Throughout this journey, we will move back and forth across that divide. We will watch Einstein in a cramped office question the meaning of time. We will let falling workers, orbiting astronauts, and speeding muons show us how relative time really is. We will follow the mathematics into black holes and confront the singularities that even Einstein distrusted. We will let quantum mechanics invade our smooth fabric with grainy, unpredictable fluctuations. We will see how our best ideas for unifying everything from loops of geometry to tiny vibrating strings keep running into the same wall. Along the way, we will keep returning to a simple guiding thread. Spacetime is not just the backdrop for the story of the universe. It is one of the main characters, and it might not be what it seems. Maybe it is a smooth continuum. Maybe it is built from discrete chunks. Maybe it is not fundamental at all, but something that emerges from deeper patterns of quantum information and entanglement. Each possibility demands a different picture of reality, and each runs into different experimental and conceptual challenges. To understand how we reach this crossroads, we need to rewind more than a century and sit with a young patent clerk who dared to ask whether time itself could be wrong. In the next part, we will step into Albert Einstein's world as he discovers that the speed of light refuses to budge and that space and time must bend instead. From that single stubborn fact, the entire modern idea of space-time unfolds. Picture a young man in a cramped office in Bern, Switzerland. His job is to stamp patents for new electrical devices, telegraph systems, early clocks, strange coils of wire that move signals around the world. During the day, he checks legal wording and diagrams. At night, he walks the streets and argues with himself about a simple question. What does it actually mean to say that two events happen at the same time? At first glance, this sounds trivial. If two bells ring at once, they ring at once. End of story. But imagine you stand on a train platform while a long train rushes past. Lightning strikes the front of the train and the back of the train. From where you stand in the middle, the flashes reach your eyes together. You declare that the strikes were simultaneous. Now jump into the story. You're sitting in the middle of the train instead, moving with it. As the lightning hits, you are rushing toward the flash at the front and away from the flash at the back. Light from the front has less distance to cover. Light from the back has more. The front flash reaches you first. You now insist the strikes were not simultaneous. Nothing about the lightning changed. Nothing about the speed of the light pulses changed. What changed was your motion. The old Newtonian picture says time is absolute. The idea of now should not depend on where you sit or how fast you move. Einstein realized that if the speed of light really is the same for all observers, then something has to give. That something is our cherished sense of a single universal time. He pushed this to an extreme with a more dramatic thought experiment. Imagine a spaceship gliding through space at half the speed of light. From the ship, you shine a beam forward. Old intuition says a person watching from far away should see that beam racing ahead faster than light because the ship adds some extra speed. Yet every experiment with real light says the same thing. No matter how fast the source moves, light always races past at the same fixed speed. The only way to make this consistent is if space and time themselves bend to hide the difference. That bending shows up in two key effects. The first is time dilation. A moving clock runs slow compared to a clock at rest. Not because it ticks sloppily, or because there is some mechanical delay, but because time itself flows differently along its path through space-time. The second is length contraction. Distances along the direction of motion shrink from the point of view of an outside observer. What looks like a 10-meter spaceship standing still might only be a few meters long when it races past at a speed close to light. This is not just clever wordplay. You can turn it into an experiment. Imagine a pair of twins. One stays on Earth. The other climbs into a ship that can travel at 99% of light speed and flies to a star and back. On the ship, their heartbeats feel normal. Their coffee cools at a normal pace. Their internal clock says a few years have passed. Back on Earth, decades may have gone by. When the travelling twin returns, they are physically younger than their sibling. The difference is not a trick of perception. It is built into the geometry of space-time. Physicists have seen versions of this in the lab. Certain unstable particles live for a tiny fraction of a second when at rest. But when you accelerate those same particles to speeds near light, they survive much longer as measured in the laboratory frame. From the particles' point of view, their internal clock is still ticking at its usual rate. From our point of view, their clock has slowed. Both descriptions are correct within each frame. The universe is just playing out the rules of space-time. We have even flown clocks around Earth on airplanes and compared them to identical clocks that stayed on the ground. The moving clocks lag behind by small but measurable amounts. These experiments line up almost eerily well with Einstein's equations. They show that time is not a shared background grid that ticks uniformly everywhere. Time is a local feature of space-time that depends on your path through the universe. Once you accept that, a lot of everyday language begins to wobble. You say a friend is watching the same sunset in another city right now, but there is no single definition of now that all observers will agree on when you include motion and distance. For someone speeding past in a spacecraft, your now and your friend's now do not line up the way you think. Different observers carve up space-time into past, present, and future in different ways, and there is no master cosmic clock to settle the argument. Einstein bundled all of this into a single framework called special relativity. The word special here does not mean impressive. It means the theory focuses on special cases where objects move at constant speed in straight lines without gravity. Within that restricted domain, the rules are crystal clear. The speed of light in vacuum is the same for everyone. The laws of physics look the same in any non-accelerating frame, and from those two statements you can derive time dilation, length contraction, the relativity of simultaneity, and a host of other results. It is one thing to write those rules in tidy equations. It is another to absorb what they imply about reality. Many scientists at the time resisted the idea that time itself could be relative. It feels much more comfortable to imagine that your watch runs slow or fast, while some invisible perfect clock ticks away the true time. Special relativity says there is no such master clock. All you have are individual world lines through space-time, each with its own proper time lived by each traveller. This shift is the first crack in the old ideas about space and time. Once time can stretch and squeeze with motion, it becomes natural to ask whether gravity might also be a symptom of geometry rather than a mysterious force acting at a distance. Einstein followed that thread for a decade, pushing himself into new mathematics and building the bridge from special relativity to general relativity. Before he could curve space-time, though, he needed one more key insight about falling bodies and weightlessness. That is where we are headed next. In the following part, we will walk with Einstein as he watches a mental image of a falling worker and realizes that someone who is falling feels no weight at all. From that odd little observation grows the idea that free fall and zero gravity are the same experience and that gravity itself might be nothing more than the shape of space-time. Einstein later said that one particular idea was the happiest thought of his life. It did not arrive in a laboratory or in front of a blackboard. It arrived as a cartoon in his mind. He imagined a worker standing on a rooftop, slipping and beginning to fall. In that instant of freefall, something strange happens. The worker does not feel their own weight. For those few seconds, their body feels as if gravity has vanished. Now imagine the worker clutching a hammer when they fall. As they drop together, the hammer does not pull down out of their hand, it just hovers next to them. If they let go, it floats beside them, falling at the same rate. From the worker's perspective, it looks as if they and the hammer are in a tiny room with no gravity at all. Of course, someone watching from the street sees a very different picture. They see both person and hammer accelerating downward under Earth's gravity. Two descriptions, same reality. This simple image led Einstein to a powerful conclusion. Being in freefall feels exactly like being in deep space far from any planets, where gravity is effectively zero. Now reverse the situation. Imagine standing in an elevator far from any stars or planets, attached to a rocket. The rocket engine fires and the elevator accelerates upward at 1 Earth gravity. Your feet are pushed against the floor. If you drop the hammer, the floor races up to meet it. Inside the sealed elevator, it feels exactly like standing in a building on Earth. From these thought experiments came the equivalence principle. Locally, meaning inside any small closed room, you cannot tell the difference between standing in a gravitational field and riding in a rocket that accelerates upward. You also cannot tell the difference between drifting freely in space and falling freely in a gravitational field. Weight is not a fundamental property of matter. It is what you feel when your motion is being forced away from your natural path through spacetime. Put this together with special relativity and something deep emerges. Special relativity says that acceleration affects how space and time behave. The equivalence principle says gravity and acceleration are the same thing when you zoom in on a small region. The conclusion is inescapable. Gravity must be a feature of spacetime itself. Whatever we have been calling a gravitational field is really just the way spacetime is curved or warped by the presence of mass and energy. Turning that intuitive picture into equations, however, was brutal. From 1907 onward, Einstein realized he needed new mathematical tools. Straight lines and simple vectors were not enough to describe curved geometry in 4 dimensions. He needed a language that could handle shapes that bend and twist in ways that look different from each point of view, yet still describe the same underlying reality. That language turned out to be tensor calculus, a branch of mathematics he had mostly skimmed past as a student. Einstein leaned heavily on his friend Marcel Grossmann, a mathematician who helped him navigate this unfamiliar territory. For years, Einstein tried candidate equations, some elegant but wrong, some clumsy but closer to the mark. He would publish a version, notice that it failed to reproduce Newton's law of gravity in the appropriate limit of weak fields and slow speeds, then retreat and try again. He knew that any new theory had to reduce to Newton's when gravity is gentle and objects move slowly, because those predictions work extremely well for the solar system. The work consumed him. Letters from that time describe an exhausting obsession. He paced, scribbled, crossed out entire pages, and circled back to ideas he had abandoned months earlier. The key was to find an equation that would tie together the geometry of space-time with the content of mass, energy, and momentum in a single balanced relationship. In late 1915, he finally arrived at a set of field equations that did exactly that. In words, the message of those equations is deceptively simple. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. A planet does not feel a mysterious force pulling it toward the sun. It is simply following the straightest possible path through a curved, 4-dimensional landscape. Those straightest paths in curved geometry are called geodesics. On the surface of Earth, for example, the shortest route between 2 distant cities is not a straight line on a flat map, but a great circle path around the globe. To visualize geodesics in space-time, people often use the rubber sheet picture. Imagine a large stretchy sheet pulled tight. Place a heavy bowling ball in the middle and the sheet dips. Now roll a marble across the surface. Its path curves toward the bowling ball, not because the ball exerts some invisible horizontal tug, but because the surface it rolls across is no longer flat. The marble tries to move straight, but straight has been redefined by the shape of the sheet. In the same way, planets and light beams try to move straight through space-time, while space-time itself is bent by stars and planets. This analogy is helpful but imperfect. The sheet is a 2-dimensional surface embedded in ordinary 3-dimensional space, while real space-time has 3 dimensions of space and 1 of time that curve without needing an extra surrounding space. The reason the marble rolls toward the bowling ball in the analogy is also partly due to Earth's gravity pulling it down, which is exactly the phenomenon we are trying to explain. Still, despite these issues, the picture captures one key idea. Gravity is geometry. A theory, even a beautiful one, is only as good as its predictions. General relativity quickly faced a long-standing puzzle. Mercury's orbit around the Sun precesses. The point of closest approach shifts slightly with each orbit. Most of that shift can be explained by the pull of other planets, but a small leftover remained unexplained in Newton's theory. Some astronomers had even proposed an unseen planet closer than Mercury tugging on it. When Einstein applied his new equations to the orbit of Mercury, they produced exactly the missing amount of precession. No extra planet required. The next test would be more dramatic and more public. General relativity predicted that light passing near a massive object would bend because it travels through curved space-time. Starlight passing close to the Sun should be deflected by a specific small angle. Under normal conditions, you cannot test this because the sun's glare washes out the stars near it. During a total solar eclipse, however, the moon blocks the sun and the hidden stars become visible for a few minutes. In 1919, 2 expeditions set out to catch such an eclipse. One team, led by Arthur Eddington, travelled to an island near the west coast of Africa. Another team set up in Brazil. They photographed the pattern of the stars around the eclipsed sun and later compared those photographs to images of the same stars taken at night months earlier. The star positions were shifted just as Einstein's theory predicted. Light had bent. When the results were announced later that year, newspapers around the world ran headlines announcing that starlight had confirmed Einstein. Overnight, the quiet patent clerk turned physicist became a global celebrity. His curved spacetime had passed its first major tests. Gravity was no longer a force acting at a distance across empty space. It was the shape of space-time itself. Yet even in this moment of triumph, trouble was already hiding in the mathematics. The same equations that elegantly explained Mercury and bent starlight also contained strange solutions that hinted at regions where space-time might collapse on itself. In the next part, we will follow those hints into the world of black holes and singularities, where the geometry becomes so extreme that even light cannot escape. Once the excitement of early successes settled, physicists started doing what they always do. They pushed the new equations to their limits to see where they might break. Among the first was Karl Schwarzschild, yes sir, a German physicist serving on the Eastern Front during the First World War. Between artillery barrages and brutal conditions, he sat down with Einstein's brand new field equations and asked a simple question. What does space-time look like around a perfectly spherical non-rotating mass in otherwise empty space? Remarkably, he found a clean, exact solution. It described how space-time curves outside a star or planet. In that solution, one particular distance from the centre of the mass turned out to be special. At that radius, the mathematical expressions in his formula went bad. Certain quantities shot off to infinity. The metric which encodes distances and times stopped making sense. That mysterious distance is what we now call the Schwarzschild radius. For the Sun, it is about 3 kilometres. For Earth, it is about 9 millimetres. Both numbers are tiny compared to the actual size of those bodies. The real Sun has a radius of about 700,000 kilometres. Earth's radius is about 6,370 kilometres. The weird behaviour in the equation seemed to happen deep inside the matter, in a region where the simple vacuum solution does not really apply. So most physicists shrugged. They treated the strange radius as a mathematical hiccup, an artifact of using an idealised model. There was no known way to compress the Sun down to 3 kilometres across, or Earth to a marble. In that era, it felt safe to treat the Schwarzschild radius as a curiosity rather than a prediction. Even Einstein was unconcerned. He disliked the idea that the equations might allow such extreme objects and wrote arguments suggesting that real matter would never collapse that far. Yet the equations themselves were relentless. If you ask what would happen to a mass that somehow did get squeezed within its own Schwarzschild radius, general relativity gives a dramatic answer. Space-time would be curved so strongly that nothing inside that radius could escape to the outside universe, not even light. The surface at that radius would act as a one-way boundary. Cross it and all future paths lead inward. At the very centre, the solution points to a singularity, a point of infinite density and infinite curvature where the equations simply fail. Einstein thought this was absurd. Infinity in physics is usually a sign that you have pushed a theory beyond where it applies. He believed that some pressure or quantum effect would step in and rescue the star before it crossed that invisible line. Stars, after all, are supported by pressure. Hot gas pushes out while gravity pulls in. When the fuel runs out, maybe electrons or neutrons would push back hard enough to prevent complete collapse. In that view, the singularity was like dividing by zero, a warning sign inside the math, not a blueprint for nature. For a while, many physicists agreed. The idea of an object so dense that even light cannot get away sounded too much like science fiction. Stars turn into white dwarfs or into neutron stars. Surely the story ends there. Then in 1939, J. Robert Oppenheimer and his student Hartland Snyder sat down to model what really happens when a massive star runs out of options. They considered a simplified model of a star made of dust, meaning matter with no internal pressure resisting gravity. When this dust sphere starts to collapse, there is nothing to hold it up. They followed the collapse using Einstein's equations and saw that once the star passes within its Schwarzschild radius, nothing in the theory stops it. From the outside, the surface of the star appears to freeze just above that radius as light struggles more and more to climb out. From the point of view of the collapsing matter, it keeps going inward until it reaches a singularity in finite time. Later calculations showed that even with more realistic physics, very massive stars cannot avoid this fate. Electron pressure can only support a white dwarf up to a certain mass. Neutron pressure can only support a neutron star up to a somewhat larger mass. Beyond those limits, no known force can halt gravity once collapse begins. For big enough stars, general relativity insists on the formation of what we now call black holes. Oppenheimer and Snyder did not use that name. The term black hole would not be coined until the late 1960s by John Wheeler. At the time, their work was mostly a mathematical curiosity. The astronomical evidence was not yet in, but the theoretical message was clear. Einstein's own equations predicted regions of spacetime that close off from the rest of the universe, with central singularities where the theory breaks down entirely. In the 1960s, Roger Penrose took this even further. He proved that singularities are not just artifacts of idealized spherical models. Under very general conditions, once a trapped surface forms, meaning a region where all light rays point inward, the formation of a singularity is unavoidable. It does not matter if the collapsing star is messy, lumpy, or spinning. If gravity wins strongly enough, space-time must pinch off. Stephen Hawking then showed that this problem is not confined to the death of stars. If you run Einstein's equations backward in time for the whole universe following the expansion in reverse, you also reach a singularity. In the language of the theory, the Big Bang itself looks like a singularity in the past. It is not a normal point in space-time. It is the edge of space-time where curvature and density become infinite and the equations lose all predictive power. Here is the unsettling pattern. General relativity passes every test we can perform in gentle regimes. It carries spacecraft to planets, guides global positioning system satellites, and describes the orbits of stars around the centre of our galaxy. Yet when pushed to its extremes, it predicts its own failure. It demands regions where time and space end in a mathematical cliff. Black holes with singular cores in the future. A cosmic singularity in the past. In a way, these monsters in the math are both a bug and a feature. They show us that the theory we have, as beautiful and powerful as it is, cannot be the last word. Somewhere near those singularities, quantum effects on spacetime must become important. A deeper framework is needed, one that softens the infinities and replaces them with understandable physics. But we do not yet know what that framework looks like. Before we tackle quantum spacetime, though, we need to understand how quantum mechanics behaves in the curved spacetime we already have. When you let quantum fields live near a black hole, something very strange happens to the idea that nothing can escape. In the next part, empty space itself will start to glow, and black holes will slowly evaporate, opening the door to one of the most troubling paradoxes in modern physics. By now, we have a universe where gravity is geometry, and singularities lurk at the edges of that geometry like mathematical warning signs. To go further, we have to invite quantum mechanics into this curved stage. That is when things stop being merely strange and start being outright rebellious. Because quantum mechanics insists on a deeply unsettling fact about reality. Empty space is not empty. In the quantum picture, what we call a vacuum is more like a restless sea. Even when you strip out every real particle you can think of, the fields that underlie matter and radiation do not sit quietly at zero. They jiggle. For tiny moments, energy pops out of the vacuum, creates a pair of particles, and then stuffs itself back in. One particle and its antiparticle appear, exist for an extremely short time, and then annihilate each other. These pairs are called virtual particles. They are allowed to exist because of a rule called the uncertainty principle. In simple language, the universe lets you borrow energy as long as you pay it back quickly enough. The more energy you borrow, the shorter the time you can keep it. For typical virtual pairs, that borrowing window is absurdly short, something like 10 to the power of minus 23 seconds. They flicker in and out so fast that under normal conditions, they leave no obvious trace except for tiny shifts in atomic energy levels that careful experiments can detect. Now imagine these quantum jitters happening right at the edge of a black hole. There is a special surface around a black hole called the event horizon. Once anything crosses this surface heading inward, it can never get back out, not even light. Now picture a virtual particle pair popping into existence with bad timing, so that one particle appears just outside the horizon and the other just inside. Normally they would meet again and annihilate. But gravity gets in the way. The particle that appears inside the event horizon is doomed. It is dragged inward, deeper into the curved space-time of the hole. Its partner, born just outside, has a chance to escape into the wider universe before the two can find each other again. To an observer far away, it looks as if the black hole has emitted a real particle. Empty space near the horizon is now a tiny factory that turns quantum fluctuations into actual radiation. This is Hawking radiation. The rough story is that the black hole pays for these escaping particles by giving up a little of its own mass. In more careful language, the particle that falls in effectively carries negative energy with respect to an outside observer, reducing the total mass of the hole, while the outgoing particle carries positive energy away. Energy is conserved overall, but the black hole shrinks very slowly as this process repeats. One of the most surprising things Hawking found is that black holes have a temperature. Not a metaphorical temperature, a literal one. They radiate like hot objects. The catch is that the temperature is inversely related to mass. The larger the black hole, the colder it is. A black hole with the mass of our Sun would have a temperature only a tiny amount above absolute zero, on the order of tens of nanokelvin. It would glow so faintly that detecting its radiation from any reasonable distance would be nearly impossible. Because it radiates so weakly, such a black hole loses mass at a glacial pace. The time it would take to evaporate completely is mind-bending, roughly 10 to the power of 67 years. The age of the universe right now is about 10 to the power of 10 years. That means a solar mass black hole would take about 10 to the power of 57 times the current age of the universe to disappear. On human timescales and even on cosmic timescales, it is effectively immortal. Smaller black holes are a different story. Imagine a black hole with the mass of a large mountain, about 1 billion tons. With that much less mass, its temperature shoots up to around 100 billion Kelvin. At that temperature, it pours out radiation furiously and evaporates in a tiny fraction of a second, releasing a burst of high-energy particles and light that would be spectacular, and probably deadly if you were anywhere nearby. Go smaller still and the evaporation becomes even more violent. Tiny black holes, if they ever formed, would be short-lived firecrackers in space-time, flashing and vanishing almost as soon as they appeared. We have no direct evidence that such primordial black holes exist, but the theory says they could, and if they do, some might be in their final explosive moments right now, sprinkled through the universe. All of this leads to a startling conclusion. Black holes are not perfectly black and they are not eternal. Given enough time, they radiate away their mass and vanish. A region of space-time that once held a singularity and a one-way surface eventually dissolves into a cloud of ordinary particles. That would be a neat and tidy story if it were not for one vicious detail. The outgoing radiation is thermal. It looks random. It does not seem to remember what fell in. Now bring quantum mechanics back to the table. One of its deepest principles is that information is never truly destroyed. The quantum state of a system evolves in a way that is reversible in principle. You can scramble information, spread it out among many particles, turn a crisp message into complicated noise. But if you knew the exact quantum state of every piece of that noise, the rules say you could, at least in theory, run the process backward and recover the original message. Information can hide, but it cannot die. Black holes appear to defy that rule. Imagine you write a detailed book full of secrets, equations, and personal stories. You throw it into a black hole. To an outside observer, the only thing that changes is the black hole's mass, spin, and electric charge. It looks exactly the same as if you had thrown in a chair or a crate of rubber ducks. The fine details of what fell in leave no imprint on the outside description. Physicists often summarize this by saying that black holes have no hair, meaning they have no extra features that record the details of their diet. If black holes lasted forever, you could argue that the information is still inside, just inaccessible. The universe would keep the record even if no one could read it. But Hawking radiation ruins that escape hatch. Over unimaginably long times, the black hole evaporates. At the end, nothing remains but a bath of thermal radiation. Thermal radiation is like the glow from a hot stove. It carries energy, but no detailed memory of whether you heated water or melted chocolate on that stove. With an ordinary fire, you burn the book and get smoke and ash and heat, but at the microscopic level, the information is not truly lost. The outgoing particles remember, in an incredibly scrambled way, what went in. In principle, if you knew the precise quantum state of every molecule in the smoke and every photon of heat, you could reconstruct the book. With a fully evaporated black hole, Hawking's original calculation said no. The radiation is perfectly thermal. The information is gone from the universe, so we slam into a wall. Either quantum mechanics is wrong about information, or general relativity is wrong about what black holes do, or our understanding of both theories breaks down in the extreme conditions near the event horizon and at the singularity. That conflict is called the black hole information paradox, and it has been a major source of productive frustration for physicists for decades. The paradox turns black holes from distant curiosities into fundamental testing grounds. They are places where space-time bends as far as it can go, and quantum effects cannot be ignored. In trying to resolve what happens to a thrown book or a collapsing star, we are really asking what space-time itself is at its most microscopic level. Before we dive deeper into that, though, we are going to take a detour back to Earth and see how this supposedly mysterious space-time quietly runs the technology you use every day. Take a moment to picture the last time you used navigation on your phone. You tapped an address, watched a little blue dot, and trusted that it knew where you were too within a few meters on a spinning sphere in space. Behind that casual confidence is a quiet balancing act with space-time itself. If Einstein had been wrong about how gravity and motion warp time, your map would drift kilometers away from reality in just a single day. Your phone works at all because we have learned not just that space-time is weird, but exactly how weird. The Global Positioning System is a good place to see this. A fleet of satellites orbits Earth about 20,000 kilometers above the surface. Each one carries very precise atomic clocks and constantly beams down signals that include the exact time and its own position. Your phone listens to at least 4 of these satellites, notes when each signal arrives, and uses the known speed of light to work out how far away they were when they spoke. With a bit of geometry in 4 dimensions, it figures out where and when you are. Now, the catch. Those satellite clocks do not tick at the same rate as clocks on the ground. They live in a different corner of space-time. First, they are moving quickly. A typical Global Positioning System satellite travels at roughly 14,000 kilometers per hour relative to Earth's surface. Special relativity tells us that moving clocks tick more slowly. From our viewpoint on the ground, satellite time should lag by about 7 microseconds per day. If that were the only effect, their time would fall behind ours. But there is a second effect that pushes the other way. The satellites sit higher in Earth's gravitational field, farther from the planet's mass. General relativity says that clocks in weaker gravity run faster. From our viewpoint, the clocks in orbit gain about 45 microseconds per day because they are not as deep in the gravitational well as we are. Combine the two effects and the net result is that satellite clocks tick faster than ground clocks by about 38 microseconds every day. 38 microseconds sounds tiny, yet light travels about 300 meters in 1 microsecond. If the system ignored relativity, the timing error would turn into a position error that grows by roughly 10 kilometers per day. After a short time, your phone would insist you're in the wrong city. Engineers do not treat this as an abstract curiosity. The satellite clocks are deliberately tuned on the ground so that once they are in orbit and both effects kick in, their tick rate matches Earth time as seen from receivers on the surface. Every time you navigate to a coffee shop, you are using general relativity. Relativity also sneaks into places you might not expect, such as the color of your jewelry. Gold is the only metal that looks richly yellow instead of silvery. The reason traces back to how electrons move in the strong electric field of a heavy nucleus. Gold atoms have 79 protons. Their innermost electrons are pulled so close and move so fast that their motion is a noticeable fraction of the speed of light. At those speeds, special relativity gently reshapes the allowed energy levels for those electrons. When white light hits gold, electrons absorb certain frequencies and then re-emit others. For most metals, the pattern of energy levels means they mostly absorb light in the ultraviolet range, which our eyes do not see, and reflect visible light evenly. They look silvery. In gold, relativistic shifts pull some of those absorption lines down into the blue part of the visible spectrum. Blue light gets eaten more than red or yellow. What comes back to your eyes is white light minus some blue, and your brain interprets that as yellow. If not for relativistic corrections, gold would be just another silver-coloured metal. Mercury, the only metal that is liquid at room temperature, owes its strange behaviour to relativity as well. Mercury atoms have 80 protons. Their innermost electrons are pulled even tighter and move even faster than those in gold. Relativistic effects contract certain electron orbits and change how strongly Mercury atoms can bond to one another. The bonds between atoms end up weaker than you would expect from a simple non-relativistic calculation. The result is a low melting point. Instead of a solid chunk, you get glistening liquid droplets in a thermometer. Relativity sits in every shimmering pool of mercury. If we zoom out from individual atoms to the global internet, spacetime shows up again. Long-distance communication relies on pulses of light travelling down fibre optic cables that thread continents and oceans. Financial markets, for example, move money based on signals that are timed to fractions of a microsecond. Clocks at different locations must stay synchronized even though they sit at different altitudes, move with Earth's rotation, and sometimes ride on satellites. Engineers use relativity-based corrections and satellite time standards to keep the whole network in step. At these speeds and scales, if you ignored the way gravity and motion affect time, your carefully timed signals would slowly slip out of tune. Then there are the machines that do not just correct for space-time, but measure its ripples directly. The Laser Interferometer Gravitational Wave Observatory, often shortened to LIGO, is basically a gigantic ruler for space-time itself. Each L-shaped detector has 2 tunnels 4 kilometers long, with mirrors at the ends and lasers bouncing back and forth between them. The idea is simple in spirit. If a gravitational wave passes through, it will very slightly stretch space along one arm and squeeze it along the other. That change alters how long it takes the light to make the round trip. The scale of what LIGO can detect is almost absurd. A strong gravitational wave from colliding black holes might change the length of those 4-kilometer arms by less than a 10,000th of the diameter of a proton. Yet by comparing the returning light waves from the 2 arms and watching for minute shifts in their interference pattern, LIGO can spot those changes. When the first clear signal appeared, it was a direct sign that space-time is not just a static backdrop, but a medium that can flex and vibrate. If you put all of this together, a pattern emerges. Space-time is not only part of grand, distant phenomena like black holes and the Big Bang. It shapes the colour of your wedding ring, the flow of mercury in a thermometer, the timing of data through submarines of glass under the sea, and the chirps heard by kilometre-scale laser instruments. We live inside this geometry and build technology that only works because we have learned to speak its language. Yet every one of these successes raises the stakes of our ignorance. We can write equations that tell satellites how to tick and predict exactly how much a gravitational wave will nudge a mirror. But we still do not know what the underlying fabric really is. In the next part, we will leave Earth once more and listen to Spacetime ring as massive stars collide, then watch it glow around black holes in images that look almost unreal. Those observations confirm Einstein's picture, while also sharpening the question that started this journey. What is it that is actually bending? For most of history, the universe was silent. We could see light from stars and galaxies, but space itself seemed mute. Then a set of enormous machines on Earth heard something that sounded almost like a bird call in the dark. A faint rising note lasting only 1/5 of a second. What those machines actually heard was space-time itself ringing as 2 black holes collided more than 1 billion light-years away. The detectors were L-shaped instruments, each with 2 long tunnels 4 kilometers in length, one in Louisiana and one in Washington state. A laser beam was split and sent down both arms, bounced off mirrors, and then recombined. As long as the arms stayed exactly the same length, the light waves lined up in a pattern that stayed still. But if a gravitational wave passed through, one arm would be stretched very slightly and the other squeezed. The returning light would fall out of sync by a tiny amount, changing the pattern. On a September morning in 2015, that pattern shifted in a way no one had ever seen before. The signal swept up in frequency and amplitude like a quiet musical note sliding higher and louder before suddenly cutting off. After months of checking every screw, cable, and possible source of noise, the team announced that they had caught the sound of two black holes spiraling together and merging. From the shape of the signal, physicists could work backward to what happened. The two black holes were each around 30 times the mass of the Sun. For eons, they orbited each other, slowly radiating energy through gravitational waves and drawing closer. In their last few orbits, they were whipping around at close to half the speed of light. When they finally crashed together, they formed a single larger black hole and released energy equivalent to converting several suns entirely into gravitational waves in less than a second. That energy rippled outward at the speed of light, stretching and squeezing spacetime as it went. By the time it reached Earth, more than 1 billion years later, the change in length of LIGO's arms was smaller than a 10,000th of the width of a proton. Yet the detectors registered it. It was as if the universe had whispered and we had heard it. Since that first detection, those observatories and their partners in Italy and Japan have picked up dozens more signals. Most come from black hole pairs of different masses. They have revealed a population of intermediate mass black holes, heavier than typical dead stars yet lighter than the giants that sit in galaxy centers. From details in the signals, physicists can infer how fast the holes were spinning and whether their spins were aligned or random, which hints at how these pairs formed. Some likely grew up together as massive stars that died side by side. Others may have met later in crowded star clusters and captured each other in gravitational dances. Then in August 2017, something even more dramatic happened. The detectors picked up a different kind of signal, longer and more complex, from a pair of neutron stars spiraling together. Neutron stars are the ultra-dense corpses of massive stars, with more mass than the Sun squeezed into a sphere about the size of a city. When they merge, they do not just shake space-time, they also light up the universe. Within seconds of the gravitational wave detection, automated alerts went out to telescopes around the world and in orbit. Observers scanned the area of sky where the signal had come from. Within hours, they found a new point of light in a distant galaxy. It brightened and changed color over days. Gamma-ray telescopes saw a brief burst. Optical telescopes watched the glow fade from blue to red. Radio telescopes later picked up the expanding debris. This was a killer nova, the explosive aftermath of two neutron stars colliding. The conditions in that inferno were so extreme that atomic nuclei were smashed together and rebuilt into heavier elements. Theoretical models had long suggested that many of the heaviest elements in the periodic table are forged in events like this. Now the mixed signal of gravitational waves and light confirmed it. When you look at a gold ring, you're wearing the ashes of dead stars that once spiraled into each other in some long vanished galaxy. Neutron star mergers flung that gold into space where it cooled, mixed with gas and dust, and eventually became part of the cloud that formed our Sun, planets, and bodies. Gravitational wave astronomy turned that story from plausible guess to observed fact. If gravitational wave detectors let us hear Spacetime ring, another project has let us see its most extreme warping. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. To do this, they used radio telescopes scattered across Earth, from Hawaii to Chile to Spain to Antarctica, all observing the same target at the same time. Each telescope recorded radio waves at a wavelength of about 1 millimeter, where the hot gas swirling near black holes glows brightly. The signals were time-stamped with atomic clocks and stored on hard drives, which were then physically carried to central computers. There, supercomputers lined up the data as if all the telescopes were pieces of one enormous dish the size of Earth. The larger the dish, the finer the details you can resolve. An Earth-sized telescope has enough resolution to read a newspaper on the Moon. The target was the supermassive black hole at the center of a galaxy called Messier, 87.55 million light-years away. The reconstructed image shows a ring of radio lights surrounding a dark center. The dark region is not the hole itself, but its shadow, a silhouette created by light bending around it. The glowing ring comes from superheated gas swirling near the event horizon at nearly the speed of light. On one side of the ring, the glow is brighter, because that side is moving toward us and relativistic effects boost its apparent brightness. 3 years later, the same collaboration released an image of the black hole at the center of our own galaxy, known as Sagittarius A star. This black hole is much less massive, about 4 million suns, but much closer, around 27,000 light-years away. The image again shows a ring and a shadow that match the shapes predicted by simulations based on general relativity. What is striking about these images is that they do not just show matter, they show geometry. The way the ring is distorted, the size of the shadow, the brightness around it, all of that encodes how space-time itself is curved in the extreme environment near the event horizon. These pictures are, in a real sense, direct photographs of Einstein's equations at work. Of course, the images are not raw snapshots like a phone photo. The data from the telescopes is sparse and noisy. Turning it into an image is a kind of inverse puzzle. Given the correlations between signals at different telescope pairs, what underlying brightness pattern on the sky would produce them? Different teams used different algorithms and assumptions, but when they compared results, they all found a ring with a similar size and shape. The structure is robust, the shadow is real. Taken together, the ringing signals from LIGO and the glowing rings from the Event Horizon telescope send a clear message. Space-time is not just a mathematical convenience. It is a physical entity that can flex, ripple, and focus light. We can measure its waves, map its curves, and rely on its behavior to guide our technology. Einstein's picture has survived test after test. Yet for all this success, none of these discoveries tell us what the fabric itself is made of. Seeing a drumhead vibrate does not tell you whether it is stretched leather or synthetic film. Hearing space-time ring and seeing it cast shadows does not reveal whether it is the smooth continuum, a network of discrete pieces, or something that only seems real from far away. In the next part, we will finally ask that question head-on and follow our theories down to the smallest scales we can imagine, where the smooth surface of space-time may break into something far stranger. We have watched space-time bend starlight, guide planets, ring with the death cries of stars, and cast shadows around black holes. It behaves like a real thing. You can poke it with lasers and it reacts. You can stir it with orbiting masses and it ripples. Yet we have been very carefully dodging the most basic question. If space-time is a thing, what kind of thing is it? What is the fabric made of? In Einstein's equations, space-time is treated as perfectly smooth. No matter how far you zoom in, there is always another smaller patch with well-defined distances and times. You can divide 1 meter into 100 pieces, then into 1 trillion pieces, then into a number of pieces so large you do not even have a name for it, and the math still behaves as if space is continuous. Time is the same. Between any two moments, you can always imagine another moment in between, and another without end. Quantum mechanics tells a different kind of story about nature. At small scales, almost nothing is continuous. Energy comes in discrete chunks called quanta. Light comes in packets called photons. The angular momentum of an electron, its spin, can only take on specific values, not any value you like. Even the energy levels in an atom are quantized. Electrons do not slide smoothly between levels. They jump. It is natural to ask whether space and time themselves play by the same rules. Maybe there is a smallest possible length, below which the word distance stops making sense. Maybe there is a smallest possible tick of time below which before and after cease to be distinct ideas. Physicists have a name for the scale where they expect quantum gravity to become important: the Planck scale. The Planck length is staggeringly tiny. It is about 10 to the power of minus 35 meters. For comparison, a proton is about 10 to the power of minus 15 meters across. If a proton were blown up to the size of the observable universe, the Planck length in that scale would be about the size of a tree. The Planck time is about 10 to the power of minus 43 seconds. That is the time it takes light to travel 1 Planck length. Below that, our current theories simply have nothing sensible to say. At the Planck scale, we expect the smooth fabric of Einstein to give way to something wilder. The placid pond of spacetime turns into quantum foam. Tiny fluctuations constantly pinch and twist the geometry. Little bubbles of the curved spacetime form and vanish. The idea of a straight line path or a clear separation between space and time might dissolve. But this is a picture painted by theory and dimensional analysis, not by direct experiment. We have never seen quantum foam. The problem is energy. To probe a length scale, you need particles with wavelengths at least that short, which means very high energies. The Planck energy is about 10 to the power of 19 billion electron volts. The Large Hadron Collider, currently our most powerful accelerator, reaches about 10 to the power of 4 billion electron volts. To hit the Planck scale directly, you would need a machine about 10,000 trillion times more powerful. That is not just expensive, it may be physically impossible to build within our universe without the machine collapsing into a black hole. So instead of smashing space-time directly, we try to reason about it indirectly. Can we take Einstein's elegant equations and quantize them the way we quantize other fields, like the electromagnetic field? Can we build a theory where the geometry itself comes in discrete units? This is the spirit behind one major approach called loop quantum gravity. In loop quantum gravity, space-time is not a continuous fabric but a network. Imagine space built from tiny loops, each about a Planck length in size, woven together into a vast web. The geometry we experience emerges from how these loops are connected. In this picture, area and volume are quantized. A surface can only have certain allowed areas. A region can only have certain allowed volumes. There is a smallest non-zero volume, below which you cannot cut space-time any further. This automatically removes some of the nastiest infinities that plague classical general relativity. At the center of a black hole, instead of a point of infinite density, the collapsing matter might reach a minimum volume and then do something else, perhaps rebound in a sort of quantum bounce. The same idea could apply at the Big Bang. Instead of a singular beginning where physics breaks, the universe might have bounced from a prior phase of contraction. These are compelling ideas, but they live in a fog of mathematical complexity. Extracting clear, testable predictions from loop quantum gravity has turned out to be hard. There is also the challenge of unification. Loop quantum gravity is built to quantize gravity itself, but it does not naturally include the other forces of nature, such as electromagnetism and the nuclear forces, in a single framework. That leaves us with a beautiful partial picture. Another approach starts from the other side. Instead of quantizing geometry directly, it asks whether all the known particles and forces, including gravity, might arise from objects more basic than point particles. This is the idea behind string theory. In that view, the objects we call electrons, quarks, and photons are different vibrational patterns of tiny one-dimensional strings. One of those patterns behaves like a graviton, the hypothetical quantum particle that would carry the gravitational interaction. In string theory, space-time is not just a stage, it is part of the cast. The theory naturally lives in more than 4 dimensions, typically 10 or 11. The extra dimensions are imagined to be curled up so tightly that we do not notice them, like tiny loops at each point in space. The shape and size of those hidden dimensions determine the types of particles and forces that appear at lower energies, including the properties of space-time itself. This gives string theory tremendous flexibility, and that is both a strength and a problem. On one hand, the theory can in principle reproduce a huge range of possible universes by choosing different ways to curl up the extra dimensions. On the other hand, there are so many possible choices that we end up with a vast landscape of candidate worlds, often quoted as around 10 to the power of 500 or more. Among the mind-numbing number of options, we do not yet have a clear principle that singles out our universe. Worse, the natural energy scale of string theory is again near the Planck energy. The predictions that would definitively confirm or rule out specific string models seem to live far beyond what we can test directly with experiments. Some features, such as a symmetry called supersymmetry, raised hopes that there might be accessible hints at collider energies, but so far those hints have not appeared. The door is not closed, but it is not invitingly open either. Both loop quantum gravity and string theory are attempts to answer the same question. What happens when you combine the quantum graininess of matter with the curved geometry of space-time? Both hint that space-time is not what it looks like at human scales. Under the smooth surface there might be loops of geometry, vibrating strings, or something even more abstract and austere. Yet both approaches struggle to give us a clear experimental handle. This is the frustrating situation at the heart of modern theoretical physics. We know the smooth picture must break. Singularities, the information paradox, and the Planck scale all shout that at us. We have powerful mathematical attempts to replace the smooth fabric with something microscopic and quantized, but we do not yet have decisive evidence that any of these attempts are right. In the next part, we will explore a third line of thinking that goes even further. It suggests that space-time may not be fundamental at all. Instead, it may emerge from something deeper that does not look like space or time, built from patterns of quantum entanglement and information. In that view, the very notion of distance is an illusion that only makes sense when you zoom out. Up to now, we have treated the deep structure of space-time as a kind of blank mystery box. We know the smooth surface must break down near the Planck scale. We know singularities and the information paradox are big red flags. The next question is how to actually replace that smooth fabric with something quantum. Two of the boldest attempts look almost opposite at first glance. One tries to quantize geometry itself, the other replaces points with tiny strings and builds space-time as part of a bigger structure. Let us start with the first camp, the loop builders. The guiding idea of loop quantum gravity is simple to state. Take general relativity seriously as a theory about geometry, then apply the usual quantum rules directly to that geometry. Instead of quantizing particles that move in spacetime, you quantize spacetime itself. Distances, areas, and volumes become operators in a quantum theory. When you ask what values they can take, you do not get a continuous range. You get a ladder of discrete rungs. In this picture, space on very small scales is no longer a smooth stage. It is more like a web. The basic objects are abstract loops of geometry tied together into networks. Mathematicians call these spin networks, but you can imagine them as a kind of cosmic mesh where each link carries a quantum number, and each node records how those links meet. The fabric of space is then the large-scale pattern woven by countless such networks. One of the surprises that falls out of this framework is that areas and volumes have smallest possible non-zero values. A surface, such as the cross-section of a black hole horizon, cannot shrink smoothly to zero area. It can only decrease in jumps of a Planck-sized unit. A region of space cannot contain arbitrarily small chunks of volume. There is a minimum grain. Like pixels in a digital image, the world looks smooth from far away, but up close there is an underlying grid. That graininess offers a natural way to tame singularities. In some loop quantum gravity models, when you follow the collapse of a black hole inward, the density and curvature reach a maximum set by the quantum of volume. Beyond that point, the classical description of spacetime fails, but instead of blowing up to infinity, the equations suggest a rebound. The singularity is replaced by a kind of bounce where the interior may continue into another region of spacetime. In similar fashion, if you apply the loop framework to the early universe, the Big Bang can become a big bounce from an earlier contracting phase. These are striking results. They tell us that if spacetime is made of loops, the dreaded infinities of classical general relativity might never actually occur. But there is a reason loop quantum gravity has not yet taken over physics. The mathematics is heavy and often tied to very simplified models. It is challenging to connect the theory cleanly to the world of the particles and forces that we know so well from the standard model of particle physics. Gravity fits in naturally. Electrons, quarks, and gauge fields are harder guests to seat at the same table. The second camp begins with a different starting point. Instead of keeping spacetime at the center, it asks whether everything we call a particle might really be a vibration of something more basic. String theory replaces point-like particles with tiny one-dimensional strings. Each string can vibrate in many ways, and each vibrational mode looks to us like a different particle. One pattern behaves like a photon, another like a quark, another like an electron. Importantly, one particular vibration has exactly the properties you would expect from a graviton, a quantum of the gravitational field. Once you add a gravity in this way, something interesting happens. You find that the theory only makes sense if spacetime has more dimensions than the 4 we experience. Typically, you end up with 10 dimensions, sometimes 11, in a more general version known as M-theory. The extra dimensions are thought to be curled up at incredibly small scales, folded into intricate shapes at every point in space. The way these hidden dimensions are folded determines the types of particles and forces that appear at low energy and the detailed properties of spacetime itself. On paper, this is very attractive. String theory automatically includes a quantum version of gravity. It provides a unified setting where all forces and matter can arise from a single underlying ingredient. It has deep mathematical consistency, meaning many of the infinities that plague naive attempts to quantize gravity do not appear in the same way. It even connects to pure mathematics in surprising ways, producing new theorems and insights that excite mathematicians who do not care at all about black holes. For a while, many physicists hoped that string theory would make crisp predictions we could test with experiments. One of those hopes involved a symmetry called supersymmetry, which pairs each known particle with a heavier partner. Quarks would have squarks, electrons would have selectrons, gluons would have gluonos, and so on. Supersymmetry would help stabilize particle masses and provide a natural candidate for dark matter. If a simple version of supersymmetry were true, the Large Hadron Collider might have seen these partner particles by now. So far it has not. The absence of easy supersymmetry signals does not kill string theory. It just pushes the likely mass of any new particles to higher energies beyond our current reach. But the bigger challenge is the landscape problem. There are an enormous number of ways to curl up the extra dimensions and switch on different fields in string theory. Each choice produces a different low-energy world with its own effective spacetime, particle content, and constants of nature. Estimates of how many such vacua exist are often quoted with powers of 10 that make even astronomers blink. With so many possible versions, it becomes hard to say why our particular universe, with its specific pattern of particles and forces, should emerge. Some theorists suggest that perhaps all of these versions exist as different regions in a vast multiverse. In that case, we observe our particular laws of physics simply because only a narrow set of laws allow stars, chemistry, and life. This is called an anthropic explanation. Many find it deeply unsatisfying because it risks turning physics from a search for unique, deeper principles into a kind of cosmic census of possibilities we can never directly visit. On top of all that, the natural energy scale where stringy effects become obvious is again near the Planck scale. Direct experimental tests seem far out of reach. In the meantime, string theory has morphed into a broad mathematical framework that can describe many different systems, not just candidate theories of everything. It has given us powerful tools to study strongly interacting quantum fields, exotic phases of matter, and even aspects of fluid dynamics. So we have two grand projects. One knits spacetime out of loops and knots and gives us discrete chunks of area and volume. The other vibrates tiny strings in hidden dimensions and promises a unified tapestry of all forces. Both can claim elegant ideas and impressive internal logic. Both can point to problems they seem uniquely suited to solve. Yet neither has delivered the decisive, testable signature that would let nature choose between them, or tell us that both are incomplete shadows of something deeper. From a distance, this might look discouraging, but for working physicists, it's more like standing in front of two partially built bridges extending into a fay. You can see the craftsmanship. You can see that they are reaching toward the same unseen shore, a quantum theory of space-time. You cannot yet see which one will connect, or whether the final path will borrow pieces from both and something else entirely. In the next part, we will explore an idea that cuts across these specific proposals. It says that space-time itself might not be fundamental in any theory. Instead, it might emerge from patterns of quantum entanglement and information, much like temperature and pressure emerge from the motion of atoms in a gas. In that view, space and distance are not the starting point. They are the collective behavior of something more abstract. We have looked at space-time as a smooth fabric, as a web of quantum loops, and as a stage for tiny strings. There is a third idea that is even more radical. It says that space-time might not be fundamental in any form. Instead, it might be a kind of illusion that appears when you zoom out from a deeper level built from quantum information. In that view, space and time are not the starting point. They are what you get when enough entangled bits of reality cooperate. This story starts at the edge of a black hole. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy. Entropy is a measure of how many microscopic states correspond to the same macroscopic object. For a gas in a box, entropy grows with volume. More room means more ways to arrange the molecules. For a black hole, the surprise was that its entropy is not proportional to its volume, but to the area of its event horizon. Double the horizon area, and you double the number of bits of information the black hole can hold. That is a very odd rule. It suggests that the information about everything that has fallen into the black hole is somehow stored on its surface, not throughout its interior. Gerard T. Hooft and Leonard Susskind pushed this idea into a bold principle. They argued that in any region of space with gravity, the maximum information content is proportional to the area of its boundary, not the volume. It is as if the world inside a region is fully described by data written on its skin. This is why people call it the holographic principle. A hologram plate is a two-dimensional surface that encodes a three-dimensional image. When you shine light on it, the pattern on the plate reconstructs the appearance of a three-dimensional object. In the cosmic version, the physics inside a volume of space could be fully encoded by quantum information living on the boundary of that volume. The apparently three-dimensional world might be like a projection of something lower dimensional. That sounds like wild science fiction, but in one special kind of universe, it has been made precise. In the late 1990s, Juan Maldacena proposed a concrete correspondence between two theories. On one side, you have a theory of gravity in a curved space with a negative cosmological constant, a kind of bowl-shaped universe called anti-de Sitter space. On the other side, you have a quantum field theory with no gravity living on the boundary of that space in one fewer dimension. The shocking part is that these two descriptions are mathematically equivalent. Every process that happens in the bulk gravitational spacetime has a mirror description in the boundary quantum theory. Black holes in the bulk correspond to hot states in the boundary theory. Gravitational waves correspond to excitations of fields on the edge. You can think of the boundary theory as encoding the bulk geometry through its pattern of entanglement. Our universe does not look like anti-de Sitter space. It appears to have a small, positive cosmological constant and is expanding, not curled in on itself like a bowl. So this exact correspondence does not directly apply to reality, but it proves something important. It shows that space-time and gravity can emerge from a lower dimensional quantum theory with no gravity at all. Geometry can be the shadow of entanglement. To see why entanglement plays such a central role, we need to revisit what it really is. In quantum mechanics, entanglement is a kind of correlation that cannot be explained by ordinary shared information. If two particles are entangled, measuring one instantly tells you something about the other, no matter how far apart they are. You cannot use this to send signals faster than light, but you cannot explain it with hidden instructions either. Experiments have shown that entanglement is a real feature of the world, not a loophole in our understanding. Now imagine not just two particles, but a huge number of quantum bits arranged in some pattern of entanglement. If the holographic ideas are right, the way those bits are entangled with each other might not just describe the geometry of spacetime, it might be the geometry. Distance between 2 points in space would translate into how strongly the corresponding bits are entangled. Regions that are highly entangled look close. Regions with little entanglement look far apart or even disconnected. This idea shows up vividly in toy models using something called tensor networks. You can build a network of simple quantum systems connected in a pattern that resembles a tiling of a curved space. When you look at how information flows through that network, it behaves like a kind of discrete spacetime with its own notion of distance and volume. If you slice away some entanglement links, the effective geometry changes. Space literally falls apart as you remove entanglement. Leonard Susskind and Maldacena took this line of thinking further with a catchy slogan often spoken as ER equals EPR. ER refers to Einstein-Rosen bridges, the simplest kind of wormhole that connects two regions of space-time. EPR refers to the Einstein-Podolsky-Rosen paper that first framed the paradox of entanglement. The proposal is that wormholes and entanglement might be two sides of the same coin. Entangled particles could be thought of as being connected by tiny quantum-sized wormholes, invisible to us but real in the underlying geometry. If that is even partly correct, then space-time is stitched together by entanglement. Long threads of quantum correlation hold distant regions together. Cut enough of those threads and the fabric tears. Add more and the fabric thickens. In such a universe, asking what space-time is made of is like asking what a warm breeze is made of. The answer is not a new substance, but a pattern of motion and interaction in something more basic. This picture also offers a new way to think about the black hole information paradox. In a holographic description, the interior of a black hole is not a separate, mysterious space where information disappears, It is encoded in degrees of freedom on the boundary theory. As the black hole emits radiation, the entanglement structure between inside and outside changes. The recent work on quantum islands and the page curve uses this holographic intuition to show how information could gradually leak out in the detailed correlations of the Hawking radiation, even though each bit of radiation looks almost thermal on its own. There is an important caveat. Much of this work is done in simplified models and mathematically nice universes that are cousins of, not identical to, our own. We do not yet have a clean holographic dual for the universe we live in. We do not yet know exactly what quantum system, if any, encodes our spacetime. These ideas are best seen as a proof of possibility. They show that spacetime and gravity can emerge from entanglement in at least some worlds, so it is not absurd to imagine the same might be true here. If spacetime really is emergent, it would be a conceptual earthquake. Space and time feel like the stage on which everything else happens. We use them to define what we mean by location, duration, and motion. To learn that they are more like temperature or pressure, properties that only make sense when you average over huge numbers of microscopic constituents, would force us to rethink what we mean by reality itself. The fundamental stuff of the universe might be quantum bits and their relationships, while spacetime is just the macroscopic story they tell when viewed from far away. In the next part, we will turn this idea toward the biggest story of all, the history of the universe itself. We will roll the clock backward from expanding galaxies to a hot early cosmos, and then push Einstein's equations all the way to the place where they break. The Big Bang, the cosmic microwave background, and the question of what, if anything, came before will take center stage. So far, we have been talking mostly about local experiments, black holes, and the weirdness of quantum spacetime. Now I want you to zoom out, way out. Imagine every galaxy you have ever seen in an image, every spiral and every fuzzy smudge. Now press rewind, run the expansion of the universe backward. Galaxies creep closer, clusters tighten, the cosmic web shrinks, temperatures climb. At some point you reach a universe so hot and dense that atoms cannot exist. Keep going and you hit a wall in our understanding, a place where our equations literally throw up their hands. We have excellent evidence that this rewind is not a fantasy. In the 1920s, astronomers measuring the light from distant galaxies noticed that almost all of them looked redder than expected. Their spectral lines, the fingerprints of chemical elements, were shifted toward longer wavelengths. The farther away a galaxy was, the stronger the shift. Edwin Hubble put this together into a simple relationship. The more distant a galaxy, the faster it appears to be receding from us. Space itself is stretching, carrying galaxies along like dots on an inflating balloon. If everything is flying apart now, then in the past it must have been closer together. Run the film backward for about 13.8 billion years, and you reach a time when the universe was packed into a much smaller volume and was unimaginably hot. This is what we mean by the Big Bang. Not an explosion inside pre-existing space, but an explosion of space itself from a hotter, denser state. One of the most beautiful pieces of evidence for this story is something you can pick up with a satellite dish tuned to the right frequency. In the 1960s, Arno Penzias and Robert Wilson were working with a large horn-shaped antenna in New Jersey. They kept detecting a faint hiss of microwave noise that would not go away. It was the same no matter where they pointed, day or night. They suspected all the usual culprits, from city interference to bird droppings inside the antenna. Nothing fixed it. What they had stumbled upon was the afterglow of the early universe. When the cosmos was only a few 100,000 years old, it was a hot plasma of protons, electrons, and light. Photons could not travel far without bouncing off charged particles, so the universe was opaque, like the inside of a glowing fog. As expansion continued, the temperature dropped. Around 3000 Kelvin, protons and electrons combined into neutral hydrogen atoms. Suddenly light could travel freely. The fog cleared. Those photons are still flying today. Over billions of years, the stretching of space has lengthened their wavelengths from visible light into microwaves. We see them now as a nearly uniform glow of microwave radiation coming from every direction, with a temperature of about 2.7 Kelvin, just above absolute zero. This is the cosmic microwave background, a baby picture of the universe when it was only a few 100,000 years old. At first glance, that glow is astonishingly smooth. No matter where you look, The temperature is almost exactly the same. But when satellites like LOMAP and Planck measured it more precisely, they found tiny variations, hot and cold spots differing by about 1 part in 100,000. Those little ripples are the seeds of everything. Slightly denser regions had slightly stronger gravity, so over time they pulled in more matter, grew denser, and eventually became galaxies and clusters. Slightly emptier regions gave up matter and became cosmic voids. Here is where the story turns strange again. If you run general relativity backward all the way, you do not just get a hot, dense early universe. You get a singularity, a point where density and curvature become infinite and the concept of time itself seems to begin. That is the Big Bang singularity. It is not a normal moment that you could step through. It is a place where the equations cease to make sense. We also find puzzles if we take the smoothness of the cosmic microwave background at face value. Regions of the sky that are now far apart, so far that light has not had time to travel between them since the Big Bang, have almost exactly the same temperature. How did they coordinate that? How did distant patches of the early universe agree on a common temperature if they were never in contact? One of the leading answers is called cosmic inflation. The idea is that a tiny fraction of a second after the start, the universe went through a brief period of insanely rapid expansion. Space doubled in size again and again in a very short time. Regions that are now far apart were once close enough to exchange heat and smooth out their differences. Then inflation stretched them away from each other faster than light, freezing in that uniformity. Inflation also gives us a natural source for those tiny temperature ripples. Quantum fluctuations in the energy field driving inflation would be blown up to cosmic scales. Regions that started with a little more energy became slightly denser. Regions with a bit less became slightly emptier. After inflation ended and normal expansion resumed, those ripples evolved under the influence of gravity into the patterns we see in the microwave background and the web of galaxies. So inflation is a wonderfully effective patch. It solves the horizon problem, which asks why distant regions look so similar. It solves the flatness problem, explaining why space appears very close to geometrically flat on large scales, and it provides a mechanism for seeding structure. The trouble is that inflation itself needs an origin story. You have to postulate a special kind of energy field and very specific initial conditions to start the rapid expansion at the right time and end it in the right way. When you push the equations of inflation all the way, you run into another weird possibility called eternal inflation. In many models, once inflation starts, it does not end everywhere at once. Instead, it keeps going in most places while occasionally stopping in small patches. Each patch where inflation ends becomes a hot Big Bang-style universe like ours, while the overall space keeps inflating. You get a multiverse of bubble universes, each possibly with different physical properties. That picture is wild, but it also dodges our original question. Even if our observable universe is just one bubble in an eternally inflating sea, we still have to ask what started the whole process, and what happens if you follow any particular bubble backward toward its beginning. General relativity keeps handing us that singularity, a place where its own authority fails. We can map the history of the cosmos with the stunning precision back to fractions of a second after the Big Bang. We can read the baby picture in the cosmic microwave background and measure the composition and age of the universe. But the very first instant is still hidden behind a theoretical fog. Many quantum gravity ideas try to replace that initial singularity with something more reasonable. Loop quantum cosmology, a spin-off from loop quantum gravity, suggests that quantum geometry effects become repulsive at extreme densities, turning the Big Bang into a bounce from a prior contracting universe. Some string-inspired models imagine that our Big Bang was a collision of higher dimensional brainers in a richer space. Others suggest that the universe might have emerged from a quantum tunneling event, out of a kind of nothing where space-time itself is a fluctuating quantum field. These proposals are imaginative, but at present they are all hypotheses without decisive observational backing. The Planck time, about 10 to the power of minus 43 seconds after the Big Bang, marks the limit of where our current theories can be trusted. Earlier than that, we are extrapolating beyond safe ground. The map stops, and the paper just says here our physics breaks. Still, it is important to notice how far we have come. A century ago, the idea that the entire universe had a hot, dense beginning was controversial. Today, we can measure its age, its composition, and the detailed pattern of ripples in its first light. We have turned the night sky into a laboratory for testing the deepest ideas about space-time, matter, and quantum fluctuations. The fact that our map has a blank at the beginning is not a failure. It is a signpost telling us that to go further we need a new kind of theory. In the next part, we will return to black holes and the information paradox, now armed with this cosmological perspective. We will see how questions about whether information survives inside a collapsing star connects to questions about whether information survived the violent birth of the universe itself, and how recent work on quantum islands hints that the fabric of spacetime and the flow of information are inseparable. We are now ready to face one of the most unsettling questions in modern physics. When the universe runs a process, does it ever truly forget? Not just practically, in the sense that it's hard to reconstruct what happened, but fundamentally. Does reality ever throw away information? For quantum mechanics, the answer is a firm no. For black holes, Hawking's calculations seem to shout yes, and in that clash, space-time itself is dragged into a kind of philosophical courtroom. Quantum mechanics is built on the idea that the evolution of a system is reversible in principle. If you know the exact quantum state now, and you have the right equations, you can work out the state in the future or reconstruct the state in the past. The technical word is unitarity, but the core idea is simple. Information is never truly destroyed. It can be scrambled and hidden across many particles, yet the universe never tears up the ledger. Now watch what happens when you mix that principle with a black hole. Drop a book into an ordinary fire. The pages burn, the ink smears, molecules fly apart as smoke and ash and heat. To you, the story is gone. Yet at the microscopic level, quantum mechanics insists that the detailed information about the book is still encoded in the exact arrangement of outgoing particles. You would need impossible precision to reconstruct it, but in principle, the universe remembers. Drop the same book into a black hole and things look worse. From far away, you do not see pages crossing the horizon. You just see the hole gain a tiny bit of mass and maybe a bit of spin. According to the no-hair idea, that is all that matters. A black hole can be fully described by mass, spin, and electric charge. There is no slot in that description for the text of your book. Many different ingoing histories give you the same final black hole. If the hole simply sat there forever, you might again shrug and say the information is not lost, only trapped beyond the horizon. The cosmic ledger is still intact, just locked in a vault you can never open. Hawking radiation turns that uneasy piece into a full paradox. Over vast times, the black hole slowly evaporates, radiating away its mass as apparently featureless thermal particles. At the end, nothing is left but a cloud of heat. Thermal radiation is the very definition of ignorance. It is a smooth distribution that knows only about temperature, not about the detailed history of what produced it. If Hawking's calculation were exact, then after the black hole is gone, there would be no trace, even in principle, of whether it had eaten a book, a planet, or a swarm of photons. The initial quantum state and the final quantum state would not be connected by a reversible map. Information would have been erased from the universe. That directly contradicts the basic rules of quantum mechanics, so something has to give. For decades, physicists split into camps. Hawking argued that maybe unitarity really fails in extreme gravitational fields, and quantum mechanics is only an approximation. Others argued that general relativity must give way, and that some more complete quantum theory of gravity will preserve information in ways we do not yet understand. Along the way, people tried to soften or twist the paradox with ideas that now sound like characters in a science fiction story. Black hole complementarity proposed that there is no single objective answer to what happens to information. To an outside observer, information is smeared across the horizon and later leaks out in Hawking radiation. To an infalling observer, the same information passes smoothly through the horizon toward the singularity. No one can compare notes, so there is no contradiction. Then came the firewall problem. If information really does emerge in the Hawking radiation, it implies highly non-trivial correlations between late radiation, early radiation, and the interior of the hole. Some clever arguments suggested that these correlations cannot all be satisfied at once if the horizon remains a calm region of empty space-time. Something dramatic must happen at the horizon. Perhaps infalling observers are fried by a wall of high-energy quanta. That would solve one problem but brutally violate the equivalence principle, which says that free fall should feel like floating. The real breakthrough arrived when physicists learned to combine ideas from holography, quantum information, and gravity in a more precise way. The key player is something called the Page curve, named after Don Page. He asked a simple question. Suppose information is not destroyed. How should the total entropy of Hawking radiation behave over time? Early on, as the black hole starts to radiate, each outgoing particle looks random and largely uncorrelated with the rest of the universe. The entropy of the radiation should grow as the whole evaporates, but if information is preserved, there must be a turning point. After roughly half the black hole's entropy has been emitted, new radiation must start to carry out information about what fell in. The entropy of the combined radiation should then decrease again, eventually dropping to zero when the hole is gone. Draw that on a graph and you get a rise and fall that looks like a hill. That is the Page curve. Hawking's original calculation gave a very different shape. The entropy only went up, never down, though the radiation stayed perfectly thermal to the end. That meant his calculation could not be the full story. The question was how to fix it without breaking everything else. In the last few years, a new set of tools has changed the game. They come from studying how to compute the entropy of quantum fields in curved spacetime, using a mixture of holographic ideas and ordinary quantum information. The recipes turn out to be subtle. When you ask about the entropy of the radiation outside the black hole, you cannot just count degrees of freedom outside the horizon. You also have to consider the possibility that some region inside the horizon is effectively part of the external quantum system because it is strongly entangled with the radiation. This region is called an island, and its boundary is chosen by a rule that picks out surfaces which make the combined entropy as small as possible. Early in the evaporation, the island is trivial. The radiation is young and barely entangled with the interior. As time passes, the best choice for the island grows. At around the Page time, roughly when half the entropy has been emitted, the island suddenly jumps to include most of the interior of the black hole. From that moment on, the entropy of the radiation plus its island starts to decrease. The full Page curve emerges naturally from the calculation. In this picture, information is never destroyed. It is encoded in extremely delicate correlations spread across the Hawking radiation and the interior region that acts as its island. Late radiation is not perfectly thermal. It carries subtle fingerprints of everything that ever fell into the black hole. In principle, a godlike observer with access to all the radiation and unlimited computing power could reconstruct the ingoing state. Unitarity is saved. What does this mean for space-time? The island prescription suggests that the inside and outside of a black hole are not sharply separate in the quantum description. The boundary of the island acts like a new kind of emergent surface that depends on which observer and which quantum question you are asking. Space and time are not fixed background scenery. They are flexible bookkeeping devices that the universe uses to keep track of entanglement. Even more striking, the calculations that produce islands and the correct Page curve work in simple toy models that have precise holographic duals. That means the same process can be described either as gravity in a spacetime with a black hole, or as a purely quantum system with no gravity at all. The fact that both descriptions give the same curve is a powerful hint that spacetime and information are two views of one underlying structure. We should be honest about the limits. These results are clearest in low-dimensional models and highly symmetric situations. We do not yet have a full island-based description for realistic four-dimensional black holes like the ones LIGO hears in the Event Horizon Telescope images. We also do not yet know what these ideas say about the detailed experience of an infalling astronaut, or whether firewalls really exist. The paradox is not so much solved as reframed in a language that makes progress possible. Still, the direction is clear. The fate of information in black holes is not just a niche puzzle. It is a spotlight aimed directly at the quantum structure of spacetime. The fact that the Page curve seems to appear correctly when we treat spacetime as emergent from entanglement tells us that any final theory will probably look more like a theory of quantum information than a theory of little billiard balls moving on a stage. In the next part, we will pull back and ask what such a theory might mean for the future of physics, technology, and our understanding of reality itself. At this point, it is fair for you to ask a blunt question. So what? Why should we care whether a space-time is made of loops, strings, or invisible bits of entanglement? Your phone works, the stars still shine. and the universe keeps expanding whether or not we figure out what happens at the Planck scale. It can feel like all of this is just intellectual fireworks for specialists, but if you look at the history of physics, that feeling is usually wrong. Whenever we have unified deep ideas about nature, the world has changed in very practical ways. Think about electricity and magnetism. For most of human history, they were separate curiosities. Static electricity that made your hair stand up, lodestones that pointed north. Maxwell came along in the 19th century and showed that they are two aspects of a single electromagnetic field, and that light itself is a wave in that field. At the time, this was abstract mathematics about invisible quantities filling space. Today, everything from power grids to radio, Wi-Fi and medical imaging lives on that unification. Then quantum mechanics arrived. It began as an attempt to understand weird details in the spectrum of glowing gases and the stability of atoms. The equations were strange, full of probabilities and uncertainty. No one invented them to build smartphones. Yet out of quantum mechanics came semiconductors, lasers, magnetic resonance imaging, and the entire digital age. Every time you swipe a screen or stream a video, you're surfing on quantum rules. Relativity itself looked extremely impractical when Einstein wrote it down. It was about clocks on trains, light rays in elevators, and the geometry of the cosmos. Nobody asked for corrections to time at high speeds to make better sat-nav devices. Yet global positioning system satellites absolutely need those corrections. Nuclear energy follows from the simple relation between mass and energy. Time dilation shapes the behavior of muons in particle accelerators and of electrons in heavy atoms, which means it helps decide the color of gold and the liquid state of mercury. So when we say that understanding spacetime at a fundamental level could change everything, we are not promising warp drives, we are noticing a pattern. Whenever humans have understood a deep layer of physical law, a generation or two later, someone has figured out how to turn that understanding into technology. We do not know what the applications of quantum gravity will be, but it is a good bet they will be surprising. If space-time is quantized, in principle there might be ways to manipulate its quanta. That does not mean building a time machine in your garage. The energy scales may be so enormous that no civilization could ever reach them. But imagine even partial control, local tweaks in the rate at which clocks tick, ways to shield regions from gravitational influence, new states of matter that live closer to the quantum fabric and have exotic properties. These are wild speculations, but a century ago, so was the idea that you could hold a glass rectangle and talk to someone on the other side of the planet. Beyond technology, there is a more human reason this matters. The questions at stake are exactly the ones that used to belong only to philosophy or myth. Did the universe have a beginning? Will it have an end? Is time an objective flow or an illusion? Is the future already there, laid out in a four-dimensional block, or is it being created moment by moment? Are there other universes with different laws where nothing like us could exist? For most of history, different cultures answered these questions with stories. Creation myths, cycles of ages, cosmic eggs, infinite steady worlds. Those stories mattered. They shaped how people understood their place in the cosmos. Today we're in the strange position of being able to test our origin stories with telescopes and detectors. We can measure the afterglow of the early universe, listen to the merging of neutron stars, and photograph the shadows of black holes. Our new stories are written in equations and data, but they are still stories about who we are and where we come from. If space-time is emergent, if distance and duration are not fundamental but arise from patterns of quantum information, then our basic intuitions about reality need to be updated. We feel as if we move through time from past to future. We feel that here and there are absolute notions. In a world where space-time is a kind of large-scale illusion, those feelings would be like the feeling that a table is solid, true and reliable at our scale, but not a glimpse of the deepest layer. There is also the question of time travel. Einstein's equations allow certain exotic solutions where paths through space-time loop back on themselves. These closed time-like curves are mathematical descriptions of universes where you could in principle leave your house on Tuesday and arrive at your own front door on Monday. Whether nature actually permits such loops is still unknown. Quantum gravity may enforce a kind of cosmic censorship that protects history from paradoxes, or it may reveal that time is less like a line and more like a complicated network of connections that our brains interpret as linear, because that is what keeps us sane. The search for extraterrestrial intelligence is tangled up with space-time too. If faster-than-light travel is absolutely impossible, then any intelligent civilization will be effectively confined to its local cosmic neighborhood. Messages between stars would take decades or centuries at best. Galactic empires would be slow, fragile things. If there are stable wormholes or other shortcuts, the picture changes completely. The galaxy could be crisscrossed by routes we do not yet understand, and our expectations about isolation or connection would need to be rewritten. Only a complete theory of space-time can tell us which of these cosmic futures is even physically allowed. Finally, there is the sheer aesthetic side. Understanding space-time is not just about gadgets or survival. It is about satisfying a deep curiosity that seems built into us. Humans have always looked up and wondered what is out there and what it all means. Cave paintings of stars, ancient observatories, philosophical treatises about time and change, all the way to modern radio telescopes and gravitational wave detectors are expressions of the same urge. We now live in a time when that urge can actually push against the limits of what can be known. We have instruments sensitive enough to detect waves in space-time smaller than a proton. We have maps of the sky that reveal the universe when it was a cosmic infant. We have mathematical frameworks that suggest space-time itself might not be fundamental. This is not just another chapter in physics. It is one of the points where our species grapples with the structure of reality at the most basic level we can reach. When future generations look back, they may see our era as the moment when the smooth canvas of space-time cracked and a deeper layer became visible. Just as Newton's laws were later understood as an approximation to relativity, and classical physics turned out to be a limit of quantum theory, Einstein's space-time may be remembered as a brilliant but incomplete step toward a more comprehensive picture. In the next part, we will step back even further and ask what a completed theory of space-time would do to our picture of time, free will, and meaning. We will look at ideas like the block universe, the arrow of time, and whether a universe built from quantum information leaves any room for the familiar sense of flowing moments that shape your life. We have been talking about space-time as if we were outside it, adjusting clocks on satellites and drawing diagrams of black holes like engineers planning a bridge. But you are not outside space-time, you're made out of it. Every thought you have is a pattern of electrical and chemical events unfolding along the path in this four-dimensional structure. So when physics tells us time might not flow the way we feel it does, or that the future may be as real as the past, it is not just an abstract claim. It is a direct challenge to your sense of what it means to exist. Relativity gives us a strange picture. It says that space-time is a four-dimensional whole, a block that contains every event that ever happens. Your life is a long, thin world line, drawn through that block, starting at your birth and ending at your death. Different observers slice this block into past, present, and future in different ways depending on how they are moving. There is no single universal moment that everyone can agree is now. In that block view, the idea that time flows becomes tricky. The equations do not contain a moving spotlight that sweeps from past to future. All moments simply are. What changes is which slice of space-time a particular observer calls present. From this perspective, becoming is an illusion created by consciousness moving along its own world line, always carrying a memory of one direction and uncertainty about the other. That picture clashes with how time feels. We experience a relentless arrow from past to future. We remember yesterday, but not tomorrow. We feel that we can influence what comes next, but not what has already happened. Where does that arrow come from if the deep laws of physics mostly treat past and future symmetrically? The most robust arrow we know is tied to entropy. In everyday language, entropy is a measure of disorder. More precisely, it counts how many microscopic configurations correspond to the same macroscopic state. A neat room can be arranged in only a few ways. A messy room can be arranged in a huge number of ways. The second law of thermodynamics says that in a closed system, entropy tends to increase, not because the universe loves mess, but because there are simply many more ways to be disordered than ordered. Pour cream into coffee and stir. The molecules mix and the swirl patterns fade. In principle, the microscopic laws would allow the reverse. The cream molecules could just happen to reassemble into a neat layer on top. But that would require an astronomically precise conspiracy between trillions upon trillions of particles. It is not forbidden. It is just unbelievably unlikely. So in practice, we only ever see entropy rise. The same logic applies on cosmic scales. The early universe was hot and dense, but also remarkably simple and smooth. That was actually a low entropy state. Over time, as gravity pulled matter into clumps and structure formed, entropy increased. Stars lit up, burned fuel, collapsed, and scattered elements. Black holes formed with enormous entropy in their horizons. The whole cosmic story is one long slide from special initial conditions toward more generic, higher entropy configurations. Our psychological arrow of time appears to be tied to this thermodynamic arrow. We remember the past because low entropy states can leave reliable records in higher entropy states. A fossil, a photograph, a memory in your brain all are imprints that form as entropy increases. You do not have records of the future because those higher entropy configurations have not yet formed. In a block universe view, those future configurations exist within the four-dimensional structure, but from your vantage along your world line you have not reached them yet, and no records of them exist in your current slice. Quantum mechanics adds another twist. At the level of the wave function, the evolution is still reversible, but when you include measurement and decoherence, you find that quantum correlations get distributed into the environment in a way that is effectively irreversible. Once information about a quantum state has leaked into countless environmental degrees of freedom, it becomes practically impossible to reverse the process. That too gives a direction to time. Where does this leave free will? In a strictly classical block universe, if you knew the complete state of the cosmos at one moment and the laws of physics, you could compute in principle everything that will ever happen. Your future choices would then be encoded in the present configuration. Your sense of deciding would be part of the unfolding story, not a force outside it. That picture is unsettling, but quantum mechanics does not automatically rescue us. Quantum events include genuine randomness. Even with perfect knowledge of a quantum state, you can only predict probabilities for certain outcomes. On its own, randomness is not the kind of freedom most people want. A choice that is partly random is not more meaningful than a choice that is fully determined. The philosophical debate about free will in a universe governed by quantum laws is less about physics and more about how we define will, self, and choice. What physics can say is this: whatever free will is, it must live comfortably inside the patterns allowed by physical law. It cannot be a ghost pushing atoms around in violation of conservation rules. But it might be an emergent property of complex information processing in brains built out of quantum fields and curved spacetime, the way the solidity of a table emerges from electromagnetic forces in mostly empty atoms. From that viewpoint, asking whether your decisions are truly free might be like asking whether the temperature of a gas is truly real. It is not fundamental, but it is not meaningless either. If spacetime itself is emergent from quantum entanglement, the block picture becomes even more subtle. The full quantum state of the universe would encode many possible histories and futures in superposition. Spacetime, with its familiar notion of a timeline, would emerge only when you look at certain coarse-grained, classical-like branches. The flow of time and the sense of a single unfolding history would then be features of those branches, not of the deepest level of description. This sounds dizzying, but it also has a strange kind of consolation. You're not wrong to feel time flowing. You're not wrong to experience a present that moves. Those are accurate descriptions of what it is like to be a certain kind of information processing pattern embedded in a universe with an entropy gradient. Physics does not take that away. It just adds extra layers showing how your experience fits into a larger structure where past, present, and future are all part of one interconnected whole. Once you see time that way, even ordinary experiences change flavor. A sunset becomes not just a daily event, but a slice through a four-dimensional path of Earth's orbit and rotation, written into space-time by gravity and the initial conditions of the solar system. Your memories become physical records on a particular world line, tracing a path through a geometry that was set in motion long before you were born, yet still open in its details because of quantum uncertainty and the staggering complexity of interacting particles. In the final part, we will step back from all the technicalities and look at the big picture one more time. We will ask where the search for a quantum spacetime might lead, what it means for our place in the cosmos, and why living at this particular moment in scientific history is both humbling and exhilarating. Take a breath and look at where we have wandered together. We started with a simple-sounding word that hides one of the deepest mysteries in science: space-time. Along the way, we watched clocks tick at different rates on satellites and on the ground, saw stars collapse into black holes, listened to the universe ring with gravitational waves, and peered at the glowing edges of the event horizons. Every step confirmed the same thing. Einstein's picture works astonishingly well, and yet it keeps pointing beyond itself, toward a layer of reality we can sense but not yet see. Right now, physics lives in a kind of creative tension. On one side, we have general relativity, a theory that treats gravity as geometry and space-time as smooth. On the other, we have quantum mechanics and quantum field theory, which say that almost everything at small scales comes in discrete packets and is soaked in uncertainty. Both theories are tested, precise, and wildly successful in their own domains. Both fail us in the same places: at the Big Bang, inside black holes, at the Planck scale where the fabric itself should start to fray. We have candidates for the deeper story. Loop quantum gravity tries to build space from tiny grains of geometry. String theory turns particles into vibrating strands in extra dimensions and hides gravity inside their harmonies. Holographic dualities suggest that space-time and gravity can emerge from a lower dimensional quantum system with entanglement stitching the geometry together. Recent work on quantum islands and the page curve hints that information is never really lost, and that the inside and outside of black holes are more intertwined than classical pictures allow. These are not random guesses. They are carefully constructed bridges reaching out from the solid ground of what we know. Yet none of them has earned the right to be called the answer. There is no experiment yet that forces us to choose one. No decisive observation that says this is how space-time really works underneath. The cosmos is being coy. It lets us detect ripples in space-time from distant collisions, but hides the quantum structure that makes those ripples possible. It lets us see the shadow of a black hole, but keeps the true nature of its interior behind a veil of extreme curvature. That might sound frustrating, but it also means we're alive at a remarkable moment. 100 years ago, the expansion of the universe was still controversial, and black holes were considered mathematical curiosities. 50 years ago, gravitational waves were a prediction on the paper, and the cosmic microwave background was still being mapped for the first time. Today we have detectors that can watch black holes collide in real time. We have sky maps that show temperature ripples in the universe when it was a cosmic baby. We have direct images of event horizon shadows. The next steps are already being prepared. More sensitive gravitational wave observatories on Earth and in space will listen to quieter signals, from lighter black holes, from neutron star mountains, maybe even from relic waves left over from the earliest instance after the Big Bang. New telescopes will sharpen our images of black hole environments and probe deeper into the high-energy universe. Precision surveys of galaxies and the cosmic microwave background will test our ideas about dark matter, dark energy, and inflation with increasing scrutiny. At the same time, laboratory experiments are pushing at the boundaries from the other end. Quantum technologies are making it possible to manipulate entanglement in ways that were pure thought experiments not long ago. Some teams are creating analog black holes in fluids or optical systems to study Hawking, like radiation in the lab. Others are using quantum simulators to mimic aspects of holographic dualities. These are not toy games. They are ways of exploring the grammar of a universe where space-time and information are two faces of the same coin. When people talk about a future theory of quantum gravity, it is easy to imagine a single equation that solves everything and then think the story ends. Reality is usually messier and more interesting. Unifying general relativity and quantum mechanics will not close physics. It will open a new era. Just as quantum mechanics unlocked semiconductors and lasers, and relativity unlocked nuclear energy and satellite navigation, a deeper understanding of spacetime is likely to reveal phenomena we have not yet imagined. Maybe we will discover new states of matter that live close to the quantum fabric. Maybe we will find subtle limits on how precisely time can be measured. Maybe we will learn that certain wild dreams, like traversable wormholes or exotic kinds of quantum communication, are forbidden in principle. Or perhaps we will find narrow pathways where they are allowed, but only under extreme and demanding conditions. Even knowing that something is impossible can be a powerful kind of knowledge. It tells future civilizations where not to waste effort, and where the true frontiers lie. On a more personal level, these ideas reshape how we see ourselves. If space-time is emergent from quantum information, then you are not just an object moving through a pre-existing stage. You are part of the process that gives that stage its meaning. Your memories are patterns laid down as entropy increases. Your sense of time flowing is what it feels like for a particular branch of the universe to trace a path through a larger, timeless structure. That does not make your experiences less real. It makes them part of the deepest story we know how to tell. There is also a kind of quiet humility baked into all of this. We are small creatures on a small planet around an average star in a galaxy that is one speck among hundreds of billions. Yet we have managed to write down equations that predict how that galaxy moves, how black holes collide, how the universe grew from a hot, dense state to the web of structure we see today. The fact that our understanding now hits a wall at spacetime's quantum edge is not a defeat. It is an invitation. Somewhere out there in the notebooks of a student, or in the code of a simulation, or in a pattern of noise in some detector that has not yet been built, the next insight is waiting. It might be a new way to think about entanglement. It might be a clever experiment that squeezes a tiny hint of quantum gravity out of the lab. It might be a mathematical link between theories that look unrelated today. Whatever form it takes, it will let us see spacetime not just as a smooth, faithful servant of Einstein's vision, but as a dynamic, quantum object with its own microscopic life. Until then, we live on the frontier. Each time you use navigation on your phone, glance at an image of a black hole, or read about a new gravitational wave detection. You are touching the outer surface of a mystery that runs all the way down to the foundations of reality. We know spacetime exists. We can measure it, bend it, and watch it ripple. We just do not yet know what it is made of. That gap between use and understanding is not a flaw. It is the space where discovery happens. And for a curious species in a vast and puzzling universe, there is no better place to be.